If you want to learn Rust, solving real coding tasks is one of the fastest ways to improve. In this video, we will solve 25 practical Rust challenges with clear inputs, outputs, and explanations. These are perfect for beginners, junior developers, and interview preparation. We start with string fundamentals, reversing text, counting vowels, and checking palindromes. These are small interview tasks, but they reveal whether you understand Rust strings as UTF-8 data instead of simple byte arrays. This comes up in small text utilities, validation tools, and interview warm-ups. Let's write the simplest safe version. Take the input, walk through its characters, reverse them, collect them back into a string, and now we run it to check the output. Let's break down why this works. The call to chars gives us text characters instead of raw bytes. Rev flips the iterator order, and collect turns the result into a new string. That is why Rust becomes sir in the terminal. Now we show the best habit for this pattern because it prevents subtle string bugs. Use chars when you mean human-readable characters, and avoid byte indexing unless you're truly working with bytes. This keeps the code clear and safe for UTF-8 input. For practice, change the input and predict the output before running the code. Try level first, then try a word with a non-ASCII character so you can see why character iteration matters in Rust. This pattern is useful when you analyze short text input like form fields or labels. Let's keep a small vowel list. Filter the characters from developer, count the matches, and then run the code to confirm the result. Let's unpack the algorithm. Chars gives us one character at a time, filter keeps only the characters found in the vowel string, and count returns how many were kept. The word developer contains 4 vowels, so the output is 4. Now we show the stronger version to remember for real input. If users can type uppercase letters, normalize the text before comparing. That keeps the vowel test simple and avoids missing A, E, I, O, or U. For practice, update the code so it handles mixed case input, test it with developer and Rust education, and make sure uppercase vowels are counted too. Palindrome checks show up in interviews because they combine cleanup with comparison. Here we take race car, normalize it first, reverse the clean text, compare both strings, and now we run the code to see the Boolean result. Let's break down the result. The cleanup turns race car into race car by lowercasing it and removing the space. When race car is reversed, it is still race car, so the comparison prints true. Now we show the cleaner design choice. Keep normalization separate from the palindrome comparison, because then each part is easier to test. In production code, that also makes it easier to add punctuation cleanup later. For practice, try the phrase never odd or even. Then extend the cleanup so punctuation does not break the check. That turns this from a toy example into a more realistic text utility. Next, we transform strings into new strings. These tasks are common in formatting user-facing text and cleaning compact identifiers before they are stored or displayed. This is useful when formatting names, headings, tags, or generated labels before showing them to a user. Let's write a helper that capitalizes one word, use it on every word in the sentence, join the result, and then run it to check the formatted title. Let's break down the transformation. Split whitespace finds the words, map applies our capitalization helper to each word, and collect creates a vector so join can put spaces back between the words. The final string is Rust coding challenge. Now we show the best practice for this kind of string formatting. Always handle the possibility of an empty word when you pull out the first character. Even if split whitespace usually skips empty pieces, the helper stays safer and easier to reuse. For practice, change the sentence to Junior Rust Developer. Keep the same helper and make sure the terminal prints Junior Rust Developer. Then try adding extra spaces between words and see why split whitespace is helpful. This pattern is useful when cleaning compact identifiers, generated labels, or short tokens. We need uniqueness, but we also need to preserve the order from the original string. So let's combine a hash set with an output string and then run the code. Let's break down the keyline. Insert returns true only when the character is new to the set. That means B, A, and N are pushed once, while the later A and N characters are skipped, so the output is banned. Now we show the best structure for this problem. Use one data structure for lookup and another for output order. A hash set gives fast membership checks, while the string keeps the characters in the exact order you decide to push them. For practice, change the input to Mississippi and predict the result before running it. Focus on the first time each character appears, because that is the order your output should keep. In this section, we solve practical string analysis problems. We will count characters, preserve order, and compress repeated data with small Rust programs. Here's the task. Given a short word, find the first character that appears only once. This pattern shows up when a token or message has one meaningful, unique marker. We write a helper that counts characters with a hash map. Then we run through the string again and print the first count equal to 1. Now let's run it and look at the output. Let's break down why this works. The word Swiss has two characters, but W appears only once, and it is the first unique character in the original order. The hash map gives us the counts, and the second loop gives us the correct position-based answer. The best practice here is to use two passes when you need both counts and original order. Trying to solve both at the same time usually makes the code harder to read. This version is simple, predictable, and easy to explain in an interview. Now try a small variation yourself. Change the input to AABBCDD and confirm that C is printed. After that, test a string where every character repeats and make the program print a friendly message when there is no unique character. Here's the task. Convert AABBC into a 3B2C1. This is a small version of run length encoding, where each group of repeated neighboring characters becomes the character plus its count. We keep one current character, count how long the run is, and flush the group whenever the character changes. Now we run it and check the compressed string. Let's break down the result. The first three characters are A, so we write A3. Then we see two B characters, so we write B2, and the last C appears once, so we write C1. The important best practice is to flush the final group after the loop. The loop only writes a group when it sees the next different character. At the end, there is no next character, so we must write the last run manually. Now try a practical variation. Update the function so it returns the original string when the compressed result is not shorter. Test it with ABC, because compressing that into a 1B1C1 is longer and less useful. Now we move into string parsing. These tasks use vec stack behavior, splitting, trimming, and token extraction from realistic text inputs. Here's the task. Validate two bracket strings, one correct and one broken. This is a classic parsing pattern because the most recent opening bracket must be closed first. We push opening brackets into a vec and pop from it when a closing bracket appears. Now we run both inputs and compare the results. Let's break down the two results. In the first input, every closing bracket matches the most recent opening bracket, so the stack ends empty. In the second input, the code sees a closing square bracket while the top of the stack is an opening parenthesis, so it returns false immediately. The best practice is to return false as soon as a mismatch appears. There is no need to keep parsing after the structure is already invalid. This keeps the parser short and avoids extra state. Now try extending the parser. Let it ignore normal text, numbers, and operators, then test it with an expression like sum. The bracket logic should stay exactly the same. Here's the task. Turn one exported row into clean fields. Real text data often has extra spaces, so splitting is only the first step. We split on commas, trim each field, convert it into an own string, and collect everything into a vec. Now let's run it and inspect the vector. Let's break down the output. The comma split gives us 3 pieces, but each piece may still contain spaces. Trim removes those spaces, so the vector contains Alice, 30, and engineer without messy white space. The best practice is to trim after splitting, not before. Trimming the whole line only removes spaces at the very beginning and end. Trimming each field cleans the data that users and exports usually produce. Now try a small variation. Add a fourth field like remote with extra spaces around it. The parser should still return a clean vector with 4 strings. Here's the task. Pull hashtags out of a normal sentence. This is a practical token parsing problem because user-written text often includes spaces, punctuation, and mixed words. We split by white space, clean each token, keep only tokens that start with a hash, and store the tag text without the hash. Now let's run it and see the extracted tags. Let's break down why the result contains only Rust encoding. Learning with and challenges do not start with a hash, so they are ignored. The 2 hashtag tokens lose their hash prefix and become normal strings in the vector. The best practice is to strip punctuation around tokens before checking the prefix. Human written text often has commas, periods, or exclamation marks next to tags. Cleaning the token first makes the parser useful beyond the perfect demo input. Now try a realistic variation. Use the sentence, ship it, #Rust, #backend with punctuation after the tags. The goal is to return Rust and backend without the punctuation. In this section, we work with the basic vector operations that show up constantly in small Rust coding interviews, finding values and filtering data. When you receive numeric data, a common first step is to find the smallest and largest value. Here we create a vector, ask the iterator for min and max, and handle the result with if let because Rust knows the vector could be empty. Now we run the code and check the output. Let's break down why this works. The vector contains 4 numbers, and iter creates a read-only iterator over them. Min finds 3, max finds 12, and the print line formats both values in one message. Now we show the safer production habit. Use pattern matching or if let when the vector may be empty, because unwrap would panic and crash the program if there is no value. For practice, try this small variation yourself. Replace the numbers with negative values like -5, 10, and 0, and confirm that min and max still give the correct result. Filtering is useful when you want to clean data before doing more work with it. Here we start with 6 numbers and use retain to keep only the odd ones. Now we run it and look at the vector after filtering. Let's break down the condition. For each number, n%2 checks the remainder after division by 2. Odd numbers have a non-zero remainder, so retain keeps 1, 3, and 5. Now we show the best use case for this pattern. Choose retain when you already own a mutable vector, and you do not need the removed values, because it avoids building a second vector. For your practice version, keep only the values greater than 3. This checks that you understand retain as a general filter, not just as an odd number trick. Now we move from basic filtering to transforming and cleaning vectors, which is where iterator style starts to feel very natural in Rust. Many real programs need to apply the same calculation to every value in a dataset. Here we keep the original vector unchanged and build a new vector of squared values. Now we run the code and confirm the transformed list. Let's break down the pipeline. Iter walks through the vector, map converts each value into a new value, and collect stores all transformed values in a vec. The original 1, 2, 3, and 4 become 1, 4, 9, and 16. Now we show the preferred style for a derived vector. When the result is a new collection, an iterator chain with map and collect is usually clearer than manually pushing values in a loop. For practice, change the calculation from squaring to tripling. Keep the same iterator structure, but replace the expression inside map. Duplicate IDs are common when data comes from imports, logs, or user input. Here we keep the original order by scanning left to right and remembering what we have already seen. Now we run it and check that only the first copy of each value remains. Let's break down the key line. Insert returns true when the value is new, so retain keeps it. If the value is already in the set, insert returns false, and retain removes that duplicate. Now we show why this is the better pattern for larger vectors. A hash set gives fast membership checks, so we avoid repeatedly scanning the result vector to ask whether a value already exists. For your practice version, try this with string IDs. The idea is the same. Keep the first time a value appears and remove later repeats. In this final section for the batch, we move into a classic interview pattern, using 2 indices to combine already sorted data efficiently. When both inputs are already sorted, sorting the combined result again wastes work. Here we use 2 indices, one for each vector, and always push the smaller current value. Now we run it and confirm that the merged vector stays sorted. Let's break down the movement. We compare left at I and right at j, push the smaller value, and advance only the index we used. When one vector is finished, the rest of the other vector is already sorted, so we append it directly. Now we show the best habit for this algorithm. Since we know the final size, with Caparisi reserves enough space up front, and the index-based traversal avoids unnecessary sorting. For practice, try vectors with different lengths. That will test whether your leftover slice logic works when one side finishes earlier than the other. Now we move into vector algorithms. These challenges are common in interviews because they test whether you can transform data without overcomplicating the solution. Leaderboards often need the runner-up value, but sorting the whole vector is more work than we need. Let's solve it in one pass by tracking the largest and second largest distinct values as options. Now we run the code and check the result. Let's break down why this works. The first 10 becomes the largest value, 5 becomes the second value, and then 8 replaces 5 as the better second value. The second 10 is skipped because this task asks for the second distinct largest number. Here's the important practice point. Define the ranking rule before coding. In real products and interviews, duplicate scores can either count or not count, and that decision changes the algorithm. For this version, duplicates are intentionally ignored. For practice, change the rules so duplicates do count. With the same input, the second largest value would become 10 because there are 2 top values in the vector. Rotating a vector is a clean way to cycle items without manually removing and inserting elements. Rust already has slice rotation methods, so we only need to calculate the effective shift. Now let's run it and look at the new order. Let's break down the output. A right rotation by 2 takes the final 2 elements and places them at the front. The values 1, 2, and 3 are shifted after them, so the result is 4, 5, 1, 2, 3. Now we show the best habit for this pattern. Always reduce the rotation with modulo. This makes the code work for small shifts, large shifts, and repeated cycles through the same vector. For a quick variation, change k from 2 to 7. Since 7 modulo 5 is still 2, the printed vector should not change. Batching data is a very common backend task, and Rust slices already give us the tool we need. We will use chunks, convert each slice chunk into its own vector, and then print the group result. Now we run it and inspect the batches. Let's break down the result. The first 2 chunks contain 2 numbers each, and the final chunk contains only 5 because there is no 6th element. Rust does not drop the remainder, it keeps it as a smaller final chunk. The best approach here is to use the standard slice API instead of handwriting index math. It is shorter, easier to read, and it handles the smaller final chunk correctly. For practice, change the chunk size to 3. Before running it, predict how many groups you will get and what the final group will contain. Next, we combine strings with vectors and maps. These are practical patterns for grouping, filtering, and comparing real text data. When text data grows, grouping is often more useful than just looping and printing. Here we use a hash map from word length to a vector of words. Then we print the lengths in sorted order so the terminal is deterministic. Now let's run it and see the groups. Let's break down the keyline. Entry asks the map for the vector at this length, and/or insert creates an empty vector only when that length is new. Then push adds the current word into the correct group. The best practice is to use the entry API when building grouped collections. It keeps lookup, insertion, and mutation in one clear flow, which is exactly what we want for map of vector patterns. For practice, add the word cat to the input vector. A new group for length 3 should appear, and that group should contain only cat. Comparing every word against every other word works, but it gets slow as the vectors grow. A hash set gives us efficient membership checks, and intersection expresses the exact operation we want. Now we run it and look at the shared words. Let's break down the result. Rust appears only in the first vector, and Go appears only in the second vector. Fast and safe appear in both, so they survive the intersection. Now we show the best practice for output that appears in tutorials, tests, or logs. Sort the final vector before printing so the same values appear in the same order every time. For practice, add systems to both word vectors. After sorting, the output should include fast, safe, and systems in deterministic order. Now we move into string data stored in vectors. These examples are common in interviews because they test whether you can transform and organize real collections. When strings live inside a vector, interviews often ask you to order them by something other than alphabetic value. Here we create a mutable vector of words, then sort it using each word length as the key. Now we run it and check whether the shortest word comes first. Let's break down the result. The closure pass to sort by key returns a number for each string, and Rust uses those numbers to order the vector. That is why fig appears first, apple second, and banana last. Now we show the best habit for this kind of sorting. Use sort by key when the sorting rule is just a simple value derived from each element, because it makes the intent clear at a glance. For practice, extend the vector with kiwi and watermelon, then change the solution so the longest word appears first instead of last. Next, we work with text processing. These tasks combine strings, iteration, maps, and careful index tracking. A frequency table is one of the most practical text processing tasks. We split the sentence into words, lowercase each word, and increment a counter in a hash map. Now we run it and print the counts in a fixed order so the output is easy to verify. Let's unpack the algorithm. Split whiteface gives us each word-like chunk, to logface makes rust and rust count as the same key, and entry lets us update the counter without writing a separate if statement. Now we show the best practice for real text input, normalize before counting, because users and documents rarely keep casing consistent. For your variation, handle punctuation. Try the input rust, rust, ! And make both words count under the same rust key. This problem is about scanning text without restarting from every position. We keep a left and right boundary for the current substring, remember where each character was last seen, and update the best length as we move. Now we run the code and the expected answer for ABC, BB is 3. Let's break down the key move. When we see a repeated character, we only move left if that repeat is still inside the current window. That keeps the scan linear instead of checking every possible substring. Now we show the best practice for sliding windows. Do not move the left boundary backward, and only advance it when the repeated character belongs to the active window. For practice, test the input pwd key. The longest non-repeating part is wake, so your program should print 3. The final section combines string and vector skills into small applied problems. These feel closer to real features you might build in a CLI tool or product search. Search suggestions are just filtering and ranking over string data. Here, we start with 4 words and a query row, keep only the words with that prefix, sort the matches, and keep the first 3. Now we run it and inspect the suggestion list. Let's break down the pipeline. Iter reads the vector without taking ownership. Copied gives us string slices in the result. Starts with does the prefix check, and truncate keeps the result small. Now we show the best practice for user-facing search. Normalize both the query and the candidate text before matching, because real users mix uppercase and lowercase all the time. For practice, add rustation with a capital R. Then change the filter so the search still finds it when the query is lowercase ru. This final task feels like a tiny CLI feature. We parse add commands into task structs, store them in a vector, then parse a done command and update one task by index. Now we run it and expect the first task to be done while the second stays open. Let's break down the flow. Strip prefix lets us recognize each command type without manual slicing, and getMute gives us a safe, mutable reference to the selected task. The printed list uses enumerate so the user sees task numbers starting from 1. Now we show the best design choice in this example. Use a struct for each task, because title and done status belong together and should move through the program as one value. For your final practice, add a list open command. It should print only tasks where done is false, which forces you to combine parsing, filtering, and formatted output. You just practiced 25 Rust problems that build real problem-solving skills. If this helped, like the video, subscribe to Dev Level Up, and write in the comments which Rust topic or challenge set you want next.